This video is for Stat 110, Module 2, Part 9, and includes a discussion of the margin of error and confidence intervals via a normal distribution. Okay, let's go ahead and get started then. So in Module 2, Part 8, we looked at obtaining the margin of error and confidence intervals using a simulated reference distribution. Here we're going to be using the normal distribution to obtain those quantities. So here is the reference distribution that we obtained in Part 8. It is the example from the Star Tribune poll. The poll had an 56% as the value reported. They had 625 individuals in their poll. And we can see when we look at a bell curve or normal curve over the top of this reference distribution that it's going to be a pretty good approximation to that reference distribution. And in fact, if we let the number of repeated iterations on our simulated reference distribution go off to infinity, that approximation is going to be even better. So what we do in practice is just use this normal curve or bell curve approximation when obtaining the margin of error or confidence interval for a proportion. So how do we go about doing that? Well, we're going to use the following formulas. So the point estimate is just the value that we obtain from the poll. We're going to have that value be denoted by the pi hat. The upper margin of error then is obtained using this equation right here. I need 1.96 multiplied by the quantity of the square root of pi hat times 1 minus pi hat, all divided by n. And n here just represents the number of people that participated in the poll. The lower margin of error is going to be that same quantity, except I'm going to use a minus 1.96. Now, once I know what the lower and upper margin of error are, I can simply add that to my point estimate and subtract that from my point estimate to obtain the upper and lower confidence intervals, or excuse me, the upper and lower endpoints for my confidence interval. So let's look at these formulas with a reference distribution in mind. So here the center of the reference distribution is at 56%. In order to obtain the upper endpoint, I would just need to take the positive margin of error, which again is given by this quantity here on the screen, and add that to the 56%. For the lower endpoint of the confidence interval, I would just take my point estimate again and subtract the margin of error quantity. Now this square root of pi hat times 1 minus pi hat divided by n is sometimes called the standard error. So this entire quantity here is called the margin of error. This part of it, underneath the radical, is called the standard error. The other value here is called the interval multiplier. And the reason we are using a positive 1.96 and a minus 1.96 is that from a normal curve, that is going to yield the middle 95% here in the middle. Recall that we build 95% confidence intervals, so we're going to want to use positive 1.96 and minus 1.96. If we wanted to go after the middle 99% of the likely values when building a confidence interval, then I'm going to need to increase the interval multiplier a little bit to stretch out this upper endpoint and to reduce this lower endpoint so that I can obtain the middle 99% of the values from my reference distribution. On the other hand, if I want the middle 90%, I'm going to reduce this 1.96 quantity. This table here on the screen produces those interval multipliers for other percentages that may be of interest. So if I wanted to capture the middle 90%, again, I would use a positive and negative 1.645 as my interval multiplier. If I wanted to build 99% confidence intervals, I would use 2.575 as my interval multiplier. But again, the most common is to build 95% confidence intervals. That's going to yield a truncation of 2.5% on the upper and lower end of the reference distribution. When truncating the upper and lower 2.5%, the interval multiplier that you're going to want to use is 1.96. So these formulas here are what we use to obtain the upper and lower confidence intervals and also the margin of error quantity. So one thing that can happen when building confidence intervals is that the binomial probability distribution can get squished to one end or the other. So here we can see that the binomial probability distribution is very close to 0% here. And what that means is that the normal or bell curve is not a very good approximation to this binomial distribution now. So you need to be careful in using this approach when the value that we're building, when the pi hat value is too close to 0, or the same thing can happen when the pi hat value is too close to 1. The distribution will be jammed up against 1, and it'll get truncated off on the right-hand side in that situation. So we have a guideline when it is acceptable to use this approach. And this guideline is when you multiply n times the pi hat value, which again is just the outcome from the survey or from the poll. So in our example, we would be taking 625 and multiply that by 0.56, I believe was our value from the poll. If that quantity is bigger than 10, and also I need to multiply n times 1 minus that 0.56, if that value is also bigger than 10, then it is acceptable to use the normal curve approximation to the binomial distribution. So that's a commonly referred to kind of a general rule of thumb of when it is okay to use this bell curve approximation to this reference distribution. Now the simulation app actually gives us a picture of that reference distribution. So you'll be able to easily identify if the bell curve is a good approximation or not. Again, if it's too close down to 0, this left side is going to be truncated, which means that the left side of that normal distribution is not going to work very well. So that's one nice thing about the simulation app, is that we can actually see the reference distribution and decide for ourselves whether or not we believe that the normal approximation is a good fit. Okay, so some questions here for you. What happens to the margin of error when the sample size is increased? Well, the sample size here is in the denominator of the standard error. So it's in the bottom here. So when this number gets really, really, really big, it's going to make the standard error very, very, very small. So my margin of error is going to be reduced in that situation. On the other hand, if I increase the interval multiplier, so instead of using 1.96, we use 2.575, which is the interval multiplier for a 99% confidence interval, then the margin of error is going to have to increase. So in a 99% confidence interval, I'm truncating less. So the margin of error is going to have to be pushed out further. So I wouldn't be truncating 2.5%, but I would be truncating 0.5%. So this upper endpoint has to be pushed out further and the lower endpoint needs to be pushed down a little further. So the margin of error would increase in that situation. How about question number 3? Why does it make sense that a 99% confidence interval should be wider than a 95% confidence interval? Well, because I am capturing the middle 99% instead of the middle 95%. So here is a common misconception about confidence intervals, is they may make a statement like, we are 95% certain that the study outcome, or the percentage from the poll, will stay between my lower and upper endpoint, whatever those are. Now this doesn't make sense because the study outcome is always exactly in the middle of my confidence interval. The study outcome will always be right in the middle of my confidence interval. So what we are doing here is not building a confidence interval for the study outcome, but we are building a confidence interval for the parameter. Again, the parameter represents the proportion, not of just those that we collected information on in our study, but when we expand our scope of inference to talk about Minnesota registered voters in general. Or the parameter represents that larger group, the percentage from that larger group. Okay, so I'm going to let you go ahead and take a moment and maybe just grab a calculator or use a spreadsheet to obtain the margin of error using these formulas. So just verify that these formulas are correct. Once we obtain the margin of error, then we can easily obtain the upper endpoint. I would just use the positive margin of error for the upper endpoint. And I can also obtain the lower endpoint of my 95% confidence interval by using the negative margin of error. The interpretation of the 95% confidence interval in the context of the example that we're looking at here would be that we are 95% certain that the proportion of all Minnesota registered voters that would support stricter gun laws in the United States goes from about 52% up to about 60%. Notice that this statement is for the proportion of all Minnesota registered voters, not just for the 625 that took our poll. We know the value for the 625 that took the poll. That was that 56%. What we're trying to do with a confidence interval is obtain what the proportion would be for all Minnesota registered voters. We can obtain those values using a spreadsheet, as I've said, or you can use a calculator. If you're going to use a spreadsheet, you just need to put an equal sign here at the beginning of your expression, and then just carefully type out the expression as shown on the screen. That will be used to obtain the margin of error here, and then I can just obtain the lower and upper endpoint by taking the 0.56, subtracting that margin of error, and adding that margin of error. Here I've actually created a graph and put that margin of error on top of that bar, that 56%. I think I've given you the instructions for doing that here, but I think I'll just go over into my spreadsheet and do that quickly for you. So over here on my spreadsheet, here's my percentages for support and oppose. If I wanted to obtain the margin of error, again, I would just use margin of error. And then here I can just type in that expression that I was just talking about. So I need to start that with an equal sign. I'm using 1.96 times, I need the square root of 0.56 times 1 minus 0.56. I need to divide all of that stuff by my sample size, which is 625. And my margin of error here is 3.9 if I round. Maybe make that a little larger so you can see that. So again, that expression looks like what I have here. If I want to create the graph, what I need to do is just highlight. I'm going to highlight my labels and also my column title here. go underneath Insert and select Chart. I'm initially going to get a pie chart. If I want to turn that into a bar graph, I can come over here under Chart Type and just change that to a bar. Now I can edit this graph as I would want. I can make that skinnier if I want. These percentages actually go from 0 up to 100. So I can click on that y-axis, and I can specify the minimum value and the maximum value for my y-axis. Now this is being expressed in percentages, so 1 here as the maximum is actually 100%. If I want to add the error bar on that, so that's the 3.9%, what I do is, again, just select the bar here. So select the bar. Underneath Customize, under my chart editor, I can select Series. Down here I have an error bar checkbox. So again, this is underneath the Series tab. I have an error bar checkbox. And I can change that to 3.9% if I want. So I can change this to percent, or have this as percent and express it as 3.9%. The other thing I could do is just do constant here. So do constant here, and then I just need to express that as a percent. So this is what I usually do here, is use constant. Then I know it's using the correct value here. Now that is the 3.9% is the margin of error for the support bar. What Google Sheets does automatically is it adds that to both the support and oppose bar. Now the oppose bar is going to have a slightly different margin of error because it's not 0.56, but it's 0.31. So what I usually do is just take off the oppose bar there. So I can double click on the bar that was there for oppose and just hit the delete key, and that'll go away. It's kind of hard to see that, it's kind of faint, but that margin of error is there on top of that bar now. And again, what that just represents is how much that bar can go up or down. Here's another example, and here what I've done is taken information from that same poll and they divided it out into two different age groups, 18 to 49 and then 50 and older. Just showing you the margin of error and 95% confidence intervals for both of those groups. Notice that the margin of error is just slightly smaller for the 50 and older group, and the reason that is because there's slightly more people, 324, instead of 299 in that group. As we discussed in the previous part, as the sample size increases, the margin of error is going to go down. Here are the interpretations for both of those intervals. Again, these are for the proportion of all Minnesota registered voters. I'll go ahead and hit pause here and let you answer these three questions. Okay, some final comments. I think I mentioned this before, but in the previous part, in order to cut your margin of error in half, you actually have to obtain 4 times as many people in your survey. So the margin of error is, practically speaking, just a measure of precision for the percentage that you're reporting in your poll. People like to obtain more precision in their outcomes. So that means you need to drive down that margin of error. People always want to make their margin of error smaller. But that comes at a cost, and in particular, you need to obtain many, many more people in order to effectively drive down that margin of error. The last thing I'll mention is that sometimes that margin of error formula is rewritten in the following structure. So this is exactly the margin of error formula. It's just that I've rewritten it as n equals this quantity. Now the reason we do this is because sometimes people want to predetermine what their margin of error might be. So suppose they are doing a poll and we anticipate that about 28% or so will respond in a certain way in the poll. And I want a 3% margin of error for that quantity. Well, you can input those values into this formula, and I can tell you, or a statistician can tell you, that you're going to need about 860 people in order to obtain that level of precision. So oftentimes we might round that up to 900 people. So your poll is going to need about 900 people in order to obtain a plus or minus 3% margin of error. So if you can give us an indication of what that percentage is going to be from the poll, then we can give you an idea of how many people you need to put into your survey in order to obtain a particular level of precision. And that idea is called the calculation for sample sizes. Okay, that does it then for Stat 110 Video Module 2, Part 9. Thank you.